Welcome to this session on network virtualization, the future of network virtualization with NSX. I'm Bruce Davey, the CTO for networking at VMware, and I'm very excited to be here in, I think, the biggest room I've ever spoken in at VMworld. For people who are still coming in, there's lots of open seats if you look around. So I'm going to try to get through the introductory material list pretty quickly because this is a fairly advanced session. I just surveyed a few people in the front row, and I think not everybody is totally familiar with NSX, but I'm going to mostly assume a decent level of familiarity. So let me just get through the boring stuff first. So most boring of all is I have a disclaimer because, as you might have guessed from the title, this talk contains some forward-looking material, and my legal people have given me this nicely worded slide to explain that you should not interpret this as a roadmap discussion. I'm going to talk about the future of technology. We're actually going to show some technology previews, which is to say things that are not yet shipping, and we don't even know if they will ship. So please, don't expect a CTO to own the roadmap. That's not the way it works. So we're just going to give you a forward-looking view of technology today and take all that stuff to heart. My marketing team slipped in this slide before I knew what was happening, so I'm going to have to go through it quickly. But the takeaway from this slide is that NSX is really getting a lot of traction. It's becoming quite a mainstream technology as more and more people adopt it. And people aren't just handing over money for NSX, they're actually putting it in production. And that number of 100 production deployments is actually well out of date by now because we keep on adding a few more every week. People are doing all kinds of cool things with NSX, which I'm going to spend the rest of this hour talking about, so I'm just going to skip over that. And we did launch NSX 6.2 this week, and a ton of new stuff in there. I've done a bit of blogging about it. We'll talk a little bit about some of those features today, but you can go and read all about the great new features in NSX 6.2, and with that introduction, we'll get on to the real introduction, where I'm going to just lay out what I hope you will get out of this session. So this is really intended to give you a sense of the future of network virtualization and the future of NSX, both a technology view and, to a lesser extent, a product view. And I hope you'll go away from this session with a pretty clear understanding of what NSX is from an architectural perspective. Because we laid the architectural foundation several years ago, really going all the way back to 2007 when Nicira was formed. I joined Nicira a few years after that, and then we got acquired by VMware just about 3 years ago. So we've been doing this for a while. The architecture is solid, and what we're seeing now is how we can build out that architecture to address more and more use cases. And one of the things I notice as I go around talking to people about NSX is there's quite a few misconceptions about NSX, and today we're going to try to disabuse you of some of those as we go through. So this is kind of the flip side of helping you understand things. We'll help you understand the things that aren't true. All right, so I'm going to really quickly recap the history of network virtualization from a use case perspective and show you the architecture in very brief detail. And then we're going to really talk about three main new innovations that NSX is enabling. First of all, we'll talk about physical networks and bare metal workloads. This is actually addressing one of those misconceptions, is that VMware only knows how to deal with virtualized workloads. Every one of our customers has some amount of physical stuff they have to deal with, and we have done a lot with NSX, and we even have some of our hardware partners here today to talk to you a little bit more about this. Oh, sorry, that was a mistake. The other two things I'm going to talk about are distributed services. Distributed services are a super fundamental part of the NSX architecture, and really what lay the foundation for all the things that we can do. You've probably all heard of the distributed firewall, but that's just the beginning of the story for distributed services. And the third thing I'll talk about relates to this slide. I'll be talking a little bit about multi-site use cases of NSX because that's actually one of the things that we're seeing starting to evolve as people do more and more with NSX. So the history of NSX is that we started off really trying to tackle a problem that we saw in large public cloud and large private cloud environments, that by 2008, 2009, it was fairly feasible at least to automate the provisioning of compute resources by spinning up virtual machines with some kind of automation tooling. But the provisioning of networks was still very, very manual, and that was obviously a bottleneck for anybody who wanted to do any kind of automated provisioning of services, whether it was a public cloud where you'd like to swipe a credit card and get some networking capabilities, or a developer cloud in a private environment. You can't have every developer's request going through some long chain of IT requests before anything happens. So automation was the first thing we went after. And initially people needed to be somewhat sophisticated and large to have figured out that networking was their key automation problem, and even to care about automation at all. So in the early days, we mostly dealt with large and sophisticated organizations who could appreciate what you needed to do to automate their infrastructure. What really changed about 18 months ago was the availability of the distributed firewall and the fact that network virtualization makes it extremely easy and cheap to spin up isolated virtual networks, as many as you want, with very, very fine isolation between different parts of the network. That capability suddenly enabled this whole new use case of providing micro-segmentation between different components within a data center. And so we went from this world of perimeter security being the only real defense you had to a world where now we can segment the data center very, very finely. And this ability to provide east-west security very conveniently coincided with a huge recognition that that was the weakness that led to all the high-profile hacks of the last couple of years, whether it was Target or the Office of Personnel Management or any other number of high-profile hacks. Most people were recognizing that micro-segmentation was what they needed to prevent that. So we were in the right place at the right time, and security suddenly became this incredibly important use case. And then, as I said, what we're seeing in this emerging class of use cases is the multi-data center use cases that enable application continuity, the ability to have an application consume resources across multiple data centers so that it can take advantage of the fact that there may be capacity here but not here, to even migrate an entire application with all of its network resources from one location to another. Something you saw a little bit of a preview of in the general session this morning, if you were watching closely. We can take entire networks, extend them from one cloud to another, or migrate an entire network from one data center to another. And that enables a whole class of new use cases. The thing to realize is that the use cases just keep getting bigger and bigger. And when we look at what our customers are doing, we find that many people are using 2 or more use cases. So last time I checked, something like 50% of our customers were doing something with security, but 70% were doing something other than security, using NSX for overlays to do things like automation or application continuity, which obviously adds up to more than 100% of our customers. So people are doing multiple things. So that's kind of what we see is a just ever-increasing set of reasons to use NSX. So this is the one slide where I'm just going to lay out the basics of the architecture before we start getting into some of the new innovations. I like to start at the bottom and focus on the data plane that NSX provides. And this is where we implement all those distributed services. Things like switching, routing, firewalling, they're all implemented in the vSwitch, inside the kernel, in the hypervisor. They scale out as you add more physical servers. And just within NSX 6.2, we have introduced a tech preview of distributed load balancing as well. So this is really fundamental to our philosophy of how we do network virtualization, that we implement distributed services in the hypervisor where they scale out and get applied right next to the virtual machines that need them. I'll say a lot more about that. We also have the NSX Edge for getting traffic in and out of the virtual space, and we have the hardware VTEPS for high throughput, high density mapping between the physical world and the virtual world, and we'll say a lot more about that. The sort of SDN component of NSX, if you like, is really the NSX controller. We gave up really talking about SDN a couple of years ago because the term had sort of been overused to the point of near meaninglessness. But the NSX controller takes one of the core ideas of SDN and says you can control a very widely distributed set of forwarding elements from a logically centralized place. But just because it's logically centralized doesn't mean that it has to be a bottleneck or a single point of failure. So the NSX controller is a cluster of machines or a group of machines. We typically use between 3 and 5 NSX controllers in any deployment. It scales out so that as your deployment gets bigger, as you have more logical networks, you can add more controller nodes. It's also highly available. You can shoot one controller node and the others will just pick up its work. You can shoot the entire controller cluster and the data plane keeps running. So it's a very highly available, scalable solution, but it gives you the ability to have a single point to control everything. So you can create, modify, manage virtual networks by only talking to one logical entity, the controller. Sitting above the controller is the manager, and the manager is the place where a human typically interacts with the system. There's a UI, and there's also an entry point for API requests that may come from other systems. So that's kind of the human interface, if you like, to NSX. And then frequently, sitting above NSX, but not always, we have some kind of cloud consumption layer. And this could be something like vRealize automation or OpenStack. We're quite agnostic about what sits up there, but something that gives you the ability to automate the requesting of resources so that you can do things like a self-service portal where a user can log in and say, I need a network. The automation system makes a series of API requests into the manager, which tells the controller what to do, which provisions that in the data plane. So that is the fastest introduction I've ever done to NSX. Like I said, this is kind of an advanced session, so we're going to start moving on to new material. If this was all new to you, you may have walked into the wrong session, but hopefully you'll get something out of the remaining 45 minutes. So what I want to talk about now is physical workloads, and both physical networks and physical workloads. This is something that we've worked on for a long time. My first VMworld was 2 years ago, and we actually did our first demos of some of the things we were doing to enable physical switches to talk to NSX 2 years ago. But if you look at all of the deployments we have today, almost all of them look like the one on the top, where we're using x86-based forwarding as a way to get traffic in and out of the virtual network between non-virtualized workloads. So if you have a mix of virtual and non-virtual workloads today, like most people do, we have a solution today that uses x86 to bring traffic from the physical world into the virtual world. The major limitation of doing it on x86 is around throughput and port density. For many deployments today, that's not an issue, but if you want higher throughput and higher port density, then a hardware form factor with one of our hardware VTEP partners is what makes sense. So this capability shown at the bottom, as I say, we demoed it 2 years ago. It's been in the multi-hypervisor version of the product, but we finally got it into NSX V with the most recent release. And so you can now choose among these two different options based on your throughput and density needs. Today, what we do is we only support L2 bridging between physical and virtual in the hardware VTEP case. So what I'm going to talk about in the next few minutes is some of the forward-looking things that we have architected. We've talked about them publicly in various mailing lists and development communities. We've worked with our partners. Again, remember the disclaimer from the beginning of the talk. These next few things are a bit forward-looking. So first of all, we've started the design and implementation of distributed logical routing in a hardware VTEP. And I'm going to walk through this in a little bit of detail because it shows not only what we're doing in the hardware VTEP space, but it also shows very clearly how a particular distributed function works. And I think this will help you understand some of the other parts of the talk a little bit better. So what we're showing here is a classic network virtualization picture, logical view at the top, physical view at the bottom. We want to just create a virtual network with a mixture of physical and virtual endpoints with a logical router interconnecting them. So down at the bottom, we've got some virtual machines sitting on hypervisors, a hardware VTEP, and they're all talking to the NSX controller. And the thing to realize here is that we're distributing the routing function out to all of those devices. So as you'll see in the next slide, there's a little bit of routing everywhere when we distribute routing out. And I'll say more about why that's important, but it means, for example, very good scalability and very efficient forwarding of packets. So this is actually a fancy version of a slide I showed last year that illustrates the process of sending a packet from a virtual workload to a physical. So they're in different subnets, so obviously routing will have to happen. And the virtual machine is going to try to send a packet to the physical. The first thing it will do is it will ARP for its default gateway. So when the ARP goes out, it hits the local vSwitch, which is acting as a distributed router component, and it will reply directly to the VM. So that's the first step. Now that virtual machine knows how to send a packet. It'll send it to the router. The router will now ARP for the destination, and that ARP will reach the physical workload, and then the response will come back. So far, we've just got all of the IP to MAC address mappings in place, sitting right next to that virtual machine. So now we can send data, and it's going to get routed by that little distributed routing component that's right next to that VM. So you might at this point say, okay, I know where the router is, it's right there on the left. But let's look at the opposite direction. This guy ARPs, it gets intercepted by the hardware VTEP. He's going to come back and reply. So now the hardware device can start sending data. Next up, the hardware VTEP will ARP for the destination, and it'll get sent out and eventually reach the destination, and now the ARP response will come back. So now the hardware VTEP knows everything it needs to know to be able to forward packets from physical to virtual, and so now data can flow. And then there's one kind of case that I haven't covered yet, which is the virtual to virtual case, and I'll skip through that quickly. The data flows that way. So the thing you should notice is that logical routing is actually happening everywhere. So that's what we mean by distributed functions. You have a logically centralized concept, a router, but it's actually implemented in these 3 different places. And depending on which packet flow you look at, you can point to different things and say, that's doing routing, that's doing routing. So this is fundamental to how we do a lot of distributed services. So the next thing I want to talk about that's also upcoming in terms of our exploration of the hardware VTEP space is how we extend some of our security capabilities into physical. So you may have seen a picture a bit like this before. NSX makes it very easy for us to segment applications along logical boundaries. And in this example, I just created 3 different microsegments for 3 different applications. And effectively what I'm saying is, I want the green VMs to be able to communicate with each other, the light blue VMs talk to each other, and the dark blue VMs talk to each other. So the thing you'd like to be able to do is to say, well, what if some of those VMs are actually physical machines? In that case, I'd still like to be able to provide this kind of segmentation and still apply security policies. And today in NSX, we provide very fine-grained security policies at the VNIC. So what can you do when you have physical workloads in the picture? Well, this is something that I've been working on personally for the last few months. And again, this is not yet in the shipping product, but the conceptual idea is shown here. We have a set of policy enforcement points around that logical router. We'd like to be able to configure policy centrally, but have it implemented in a distributed way. In the physical world, we'll create firewall rules using the distributed firewall function of NSX. And in the physical world, we'll do the next best thing, which is we'll configure ACLs on a port of that physical switch. All of this will be done under the control of NSX. You'll still configure policies using some of the grouping concepts that are already in NSX. So you can say things like, all of the devices that belong to this tier of an application get this policy. And so a lot of the capabilities that are in NSX will now get extended out to physical endpoints. And so in order to make this possible, we've been developing some extensions to the control channel between NSX and the physical hardware VTEPs. Okay, I'm going to do a quick quiz. Who knows what protocol we use to communicate with hardware VTEPs? You're not the man in the front row. Okay, I'll take it from the red shirt in the 3rd row. OVSDB, congratulations. There'll be a small, I'll try and find a prize for you. So, at the very least, a business card. OVSDB is the protocol that we use to communicate information between NSX and hardware VTEPs. And all of this work has been done in the open source community so that any one of our hardware partners, or even people who aren't our hardware partners, can go and see what we're doing and install the right capabilities on their switch. So not too long ago, I pushed a commit to OVS. It's only in my local repo at the moment. It's currently out for review. But I'm very proud to say this is the first time I've shown one of my own Git commits in a talk. So this is the change to the OVS schema, and this is kind of what it looks like if you were to go and build the OVS documentation. I'm not going to go into this in detail, but the basic idea here is that this gives us a mechanism by which an NSX controller can go and tell a hardware VTEP to configure an ACL according to a set of policies that were provided through the northbound API of NSX. So what I've shown you in the last couple of slides is how we can keep on growing the capabilities of hardware VTEPs. We have a very extensible control channel. We have a very willing and able group of partners who are implementing these things, and we're adding this into NSX as well. I feel like it wouldn't be a proper networking talk if I didn't say a little bit about tunneling. So if you look at the history of tunneling, in the early Nicira product, we had a tunneling protocol called STT, and then a couple of years ago, VXLAN kind of appeared on the scene, and people started saying, oh, how are they going to ever make STT and VXLAN work together? And the point I want you to take away is that this is just not a hard problem, and it's actually not that important. So I'm going to spend a minimum amount of time on it. I like to think of tunnels as being very similar to cables. Yes, you should use the correct cable in your data center, but it's not a fundamental architectural choice whether you use Cat5 or single mode fiber or multi-mode fiber. It may affect performance, and you shouldn't use the wrong cable in the wrong place, but it's not the fundamental architecture. So that's what I mean by the tunnels are like cables. And the most interesting thing I can say in terms of new information is that a couple of years ago, or I guess about 18 months ago, we started working on kind of one grand unified protocol, which always is the way you solve a standards problem. If you have n standards, you create the n+1th standard to solve all your previous problems. So we did this with Geneve, and Geneve is currently getting a fair amount of uptake, and so you'll start to see deployments looking like this, where we can swap Geneve for the hypervisor to hypervisor traffic, and then we could potentially keep VXLAN for as long as we need to. So don't be nervous about buying VXLAN capable hardware. It'll be something that'll work forever. But then over time, we could also see Geneve showing up there. And just to give you a sense of what's going on, first of all, again, for a networking talk, you have to have one packet header. So that's the Geneve packet header. You'll notice it looks a lot like VXLAN if you're familiar with VXLAN. The big difference is this extensible option field. And this is incredibly valuable when you implement networking in software, to be able to keep on adding new capabilities as you think of them without always respinning the hardware or the packet header format. And so if you look at the bottom of this slide, you can see we've got a lot of support for this coming up already. We've got a variety of different software implementations. It's in at least 4 different NIC vendors that I know of. It's in the switching silicon of several different vendors as well, and a bunch of monitoring tools deal with it. So this has actually come along pretty quickly, and so the main thing I want you to take away there is really just that tunneling is a bit of an evolving field, but it's not something you should lose a lot of sleep over, because we're just optimizing some of the details that are not that fundamental from an architecture point of view. The most fundamental thing is to have the flexibility of software when building your networks, and that is something we've definitely figured out how to do. Okay, so this is what's called a rhetorical question. By that I mean, I don't really want you to answer it for me. I'm going to answer it for you instead. The answer to this question is no, but let me say a little bit more. The problem with network visibility is essentially you kind of want to know what's going on everywhere in your network. And historically that's been a somewhat hard problem, because how did you know where to look? Well, one of the awesome things about network virtualization is you know exactly where to look. You ask the controller, because it's talking to every networking device in the overlay. But then you say, but don't overlays hide what's going on? Well, again, the answer is no. We've been using overlays for a long time. MPLS is a highly successful form of overlay. We know how to troubleshoot networks that have multiple layers in them. You just need to have things like tooling that can interpret both the upper layer headers and the lower layer headers. I just showed you 3 tools on the previous slide that understand how to look at an overlay header and look at the packets inside it. So tooling is absolutely important. In the next few slides, we're going to show you a little bit of information about tooling. But if you take away one thing about visibility, it should be that network virtualization makes visibility less of a problem, not more of a problem. And just to pick on another feature recently announced in NSX, we have a thing called traceflow. Traceflow lets you say, synthetically create a packet as if it came from this VM and send it towards that VM, and then show me every step of the forwarding pipeline between the source VNIC and the destination VNIC. You basically get to see switching, routing, firewalling, load balancing, physical path, load balancing, firewalling, routing, switching. Every single step of the pipeline can be displayed. It's kind of like having a debugger for networks. This is something that's never been possible before. So network virtualization is changing the laws of physics, and this is one of the ways it's doing it. So tooling is important. So if you look at NSX itself, we have a lot of built-in capabilities. if there's a thing that you can do on a physical network, you can do it in a virtual network. Whether it's NetFlow, IPFix, syslog, SNMP, all of those things are supported in virtual networks. That's how you know they're virtual networks. They look just like physical networks. Other things that you couldn't get from physical networks, like traceflow, like the port connections tool, a central CLI, are also in NSX. We have integrations with our own tools, and we're going to show you one of those in a minute. And we have integrations with a whole ecosystem of partners who are in the business of understanding both physical and virtual. So you can get this complete view from top to bottom of what's going on in your physical network, or sorry, your virtual network and your physical network. So at this point, I'm going to switch over to a demo. It's a pre-recorded demo. We don't like to be too much on the trapeze up here. But what we're going to show you is how, again, forward-looking capability, remember the disclaimer, we're going to show you some as yet unreleased capabilities that we've built on top of vRealize operations to show you the end-to-end path, physical and virtual. And to get me through this, I'm going to bring up Ken Duda, CTO and co-founder of Arista, who's been one of my great collaborators on this whole physical plus virtual journey. I'll hand it over to Ken.
Great, thanks so much, Bruce. Thank you all for coming. I'm delighted to give this demo to you to show you why it's so important when you're picking a vendor for your physical network, to pick a vendor who creates a solution that integrates properly with the virtualization environment, rather than a vendor who's trying to railroad you into a single proprietary solution. And
I have no idea who you're talking about.
Me neither. So to show you what I mean by integrate properly, I'd like to show this, this demo here. So what you have here is vRealize Operations Manager. On the left, we have the virtual environment. And on the right, we have the physical network. 2 leaf switches and 2 spine switches, just as you saw in the topology diagram in the previous slide. You also have information such as top talkers. And in the center, you have alerts. And you may notice there are quite a few alerts in this environment because it's a test environment not quite set up to best practices. But so here we see one of the most useful features of this environment, which is the traceflow feature Bruce was talking about before. You select 2 VMs, and VR Ops figures out how those 2 VMs connect, both in virtual space, where they're connected simply by a logical switch, but critically, also in physical space, where you see the complete path from VNIC to server to top-of-rack switch, ECMP routing across the spine to the egress top-of-rack switch and the egress server. And for each of those objects, you can mouse over it and see status information. And to show how this can help with troubleshooting, imagine there's a link failure, and one of your top-of-rack switches loses its connection to the spine. Here we just shut down the link, and what you can see is the leaf switch immediately turns red because we view a loss of connectivity to the spine as a critical outage. And you're trying to understand what's going on, so you'll go back to traceflow, and what you see now is a red badge on the right top-of-rack switch down there, and the loss of the alternate ECMP path because you can no longer reach that router. But thanks to equal cost multipath routing, you can see in the diagram above, the logical connectivity from one VM to the other is uninterrupted. And so now you can drill into the outage if you click on the badge and see the details of the problem, including which switch is affected, which physical interface on that switch, and then also other useful information. Like if you click on the alert for details, you'll see the time frame of when the link was down. So for each of these status indicators, you get a graph over time. It was down for a little while, it's been up for a while, and then just recently, it went down again. And that sort of contextual information can be so helpful when you're trying to troubleshoot a real-world problem. And now to show what it looks like when you resolve the issue, we go back to the switch and re-enable the interface. Of course, it was supposed to be enabled all along. And then back to vRealize Operations Manager, where you'll see the link status indication change. That the top-of-rack switch is now green once again. And if we go back to the traceflow diagram, you'll see once again that we have full connectivity restored. And so what you see here is that critical connection between the logical topology and the physical network being bridged, single pane of glass, where you can see the complete picture, virtual and physical.
All right, beautiful.
Thanks very much. Thank you.
Yeah, so that was something we threw together on Friday afternoon. Actually, literally that's when we recorded it, but it was many man hours of work went into that. So let's move on to the next section. Yeah, actually, I just want to mention too, like networking is all about open interfaces. So one of the really awesome things there is the way the VROps tool has leveraged open interfaces from the Arista switches to show the complete physical plus virtual view. And of course, NSX provides all these open APIs, which are published and very readily available for other tools to integrate with. So, again, sort of to make this point, it's not all about just having everything from one vendor. That open interfaces make it possible to build together all the components that you need. And that's really the way the modern data center looks. So, distributed services. So hopefully you've heard a lot about at least the distributed firewall, but in fact, we've been doing distributed services since day one. I mean, you probably all know about the distributed switch and distributed routing, distributed firewalling. I'm going to talk a little bit about distributed load balancing. There's a few important reasons why we kind of pound this story about distribution. Every time you add some workloads to your network, you're consuming some resources on a server. Eventually, you'll decide you need another server to accommodate more workloads. When you do that, you've immediately added more capacity to do more distributed services. So these capacity to do things like firewalling and switching and routing scales out as you add more servers. It's actually the most scalable way to do east-west firewalling. We have deployments with terabits of firewalling capacity without a single physical firewall in the deployment. So scale is super important. Secondarily, or at least second as we go across the slide, the fact that we apply services at the NIC is also incredibly important. That means that we can apply things at very, very fine granularity. So you can say things like, this web-facing machine and this other web-facing machine, even though they're in the same application at the same tier, should not talk to each other, because their job is to take traffic from the web and forward it to the next tier. So if these machines start talking to each other, I would like to block that, and I would like to know about it because it's probably a sign of something going wrong. So that's the level of granularity that you can apply if you're applying services at the VNIC, even if those two virtual machines happen to be in the same host. Additionally, because we're doing services at inside the hypervisor, we have access to all of the context within that hypervisor. So we know what operating system is running. We know the name of the virtual machine. We can even find out what users and what applications are running on that virtual machine. So we can apply contextual information to inform our security policies, our load balancing policies, in a way that's fundamentally impossible if you try to do this in a physical appliance. And finally, not to beat a dead horse here, but we get visibility that is unprecedented. The fact that you can see every packet as it leaves the VM and goes through the VNIC means you can look at how these services are getting applied. If you've misconfigured an ACL, then a tool like Traceflow can help you figure out what went wrong. So those are the reasons why we think distributed services are such a fundamental aspect of NSX. And this is just another way of looking at sort of how you would do things traditionally. You would, if you wanted a service, you would hairpin the traffic or trombone the traffic, depending on your metaphor, out to some remote box to get the service. In NSX, we can do that directly. If the two VMs are on the same host, the packets never even leave the server. If we're going between two different servers, we take the shortest physical network path between those servers to get the services applied. And then we can also use this as a point to insert additional services from our ecosystem of partners. And I'm not 100% sure that's completely up to date, but that's at least a subset of our ecosystem partners who can, in an integrated fashion, receive packets selectively from NSX and apply their own more value-add services to those streams of packets as they pass through, which means those services too can scale out and apply context and be done at a fine grain. So what I want to talk about today is a new thing that's in technology preview called distributed load balancing. So the first time I heard about this, I was a little bit perplexed, because if you think about load balancing, you imagine yourself sending a packet to a load balancer. You sort of think about there being a VIP that you want to send a packet to. So I was thinking, well, how do you distribute a function like that? But if you look at it a little bit more closely, what a load balancer does is it takes packets from one tier of an application and it forwards them to another tier of the application, but it sends them to multiple different destinations in that tier based on availability of a set of destinations. So if you think about that task, it's actually not that different than what a distributed router does. It's just that you look at different things in the packet. So for example, you might do a hash of the fields in the protocol layer header. You might say, if the protocol number is 80, then I want to load balance across these 3 different devices in the next tier. So I'm just going to send this flow that way, I'll send this flow that way, and this flow that way. So that's a function that distributes very naturally. You can still configure it in a centralized way, because that's how we think about load balancing, but implement it in a fully distributed way and get all the benefits that I've described. And if you think about the contextual information that a load balancer needs, one of the things that it needs to know is this a good destination to send a packet right now, or to send a new workload, to send a stream? And because it's sitting inside the hypervisor, the load balancer can actually be informed by things like, maybe the CPU is overloaded on this particular machine, so I shouldn't be sending more traffic to it. Maybe the VM has actually crashed. So we have better information about the health of a VM sitting inside the hypervisor than any external load balancer could possibly have. So just like with our previous examples, contextual information is very valuable and something that we get by distributing this function. So just to sort of complete the example here, the picture on the right sort of shows you what's going on physically. On the left, it shows the logical view, and you can just see how we're load balancing from one tier to the next. And in the physical view, we're just sending packets through the vSwitch across the shortest path in the data center to the destination and making sure it gets to a virtual machine that's equipped to handle that load. So I thought that was super cool when I first heard about that. So that's one of the things you can play with if you're starting to get your hands on NSX 6.2. Now, people often ask about performance when I talk about distributed services, because we're doing all these things in software, and everybody knows that hardware is faster than software, at least all else being equal. But the thing is, as I've said, the scale-out properties here kind of work in our favor. So what we've done is we've put a lot of energy into making sure that the performance of the vSwitch is very good, even as we're starting to apply additional services. And one piece of intuition here is that as you already take the packet from the virtual machine into the vSwitch and then transmit it out to the physical network, you have that packet in the cache of your CPU. Once you've got it in the cache, it's not that expensive to do some additional manipulations on the header. For example, to look at the port number to apply a firewall rule, or to look at some flow information to do a load balancing operation. The most expensive thing is getting the packet out of main memory into cache, and you already paid that cost. So this is why we get such good performance numbers. These are actually not that cutting edge. This is numbers we collected in 2014 on a generation of hardware that's definitely not at the bleeding edge. But you can see, for most moderate to long packets, we're able to sustain line rate forwarding, even with quite large numbers of firewall rules. And I'm not going to say there's no performance tuning you need to pay attention to, but the main thing to realize here is that we can sustain very, very high performance, and if you want more performance, you scale out. So this will actually get you to places that a physical device won't get you to. So this leads to my next kind of rhetorical question. This is actually where I'm at risk of getting into a rant. So how many people here have heard something about DPDK? Yeah, maybe half, the third of the audience. Not as many as I would have guessed, maybe. How many people here have heard that DPDK is this sort of magic pixie dust that makes everything go faster? Yeah, quite a few of those. So that's kind of the myth I want to disabuse you of right now. DPDK is an awesome piece of technology with awesome marketing. Kind of like NSX, you might say. But the thing to realize is it's not actually magic. That most of what DPDK does, it stands for Data Path Development Kit, or Data Plane Development Kit. What it actually does is it combines a whole lot of techniques, most of which were researched over the last 10 years, to avoid incurring big penalties for going out and accessing main memory. So there's a whole lot of techniques, polling rather than taking interrupts, staying in user space rather than switching between kernel and user space, using giant pages so you don't have TLB misses. I could go on, but the main point is there's a collection of techniques. They're mostly pretty well known to people who optimize performance for a living. So it wasn't like we woke up one day and said, oh my goodness, we never understood performance until DPDK came along. It was like Intel very kindly packaged up a set of techniques and made them available to a wide community of developers. So what does this have to do with the previous slide? Well, we don't today use DPDK in vSphere, but we get pretty good performance because you don't necessarily need DPDK to get good performance. However, we do have ongoing work to optimize the performance of our x86 forwarding between physical and virtual. And so I spent a lot of time talking with one of the engineers who's developing that x86 forwarding. He's never going to get packets to go as fast through an x86 server as you could get them to go through an equivalent size top of rack switch. But he can get very, very high throughput, like on the order of many tens of gigabits from a single server. And he's using DPDK because it's a really convenient way to get all these performance tricks. But he explained to me, if we just did that, we still wouldn't get the performance we want. We had to use a flow cache as well. I'm getting reminded that I have 10 minutes left until we start Q&A, if we feel like that. So the point here is that we have lots of things going on to take advantage of DPDK, but if you wanted to sort of take away just one thing from this section of the presentation, it's that the switching performance we get today is incredibly good, and it meets the needs of the vast majority of workloads. We may at one point find a need to do more with vSphere switching performance, and we certainly will focus on the edge performance, but today performance is really great, and DPDK is interesting, but not like a magic bullet that you need to add to get good performance. All right, so that leads me on to my last section. So this is going to be a little bit superficial, but just because of the amount of time we have available. There are several sessions that spend the entire hour talking about multi-data center environments. And this is, I think, super exciting because it's kind of the next big frontier for NSX. So I wanted to talk about it, but I obviously can't go very deep. I thought what I would start by doing is just give you kind of the big picture, because there's so many different things going on in this space. And I just wanted to get a Star Trek reference in somehow. So and if you don't understand that, don't worry. So over on the left, we have kind of things that happen today. People are putting NSX in production to span across multiple data centers. If you want to learn how to do that, I'll give you some references to other talks. People are using NSX today to do disaster recovery. This has actually just got better this week because our SRM tool, Site Recovery Manager, now knows how to take a snapshot from NSX of a particular network, copy it to your backup site, and then bring it up when you have a DR event. This is a really important thing that network virtualization does. Virtual networks are just like virtual machines. They're implemented in software. They're a bag of bits. You can snapshot them. You can clone them. You can move them around. So you can now take your complete running active data center, make a perfect copy of it, complete with all the network services, and put that in your DR data center and run exactly the same applications with the same networking. No re-IPing, just run exactly the same things in both places. Radically shifts the time to recover for a DR. Now, what about federation? I'll talk about that in the next slide. Some people know me as that MPLS guy. That's sort of an industry thing I picked up over the years. So I'm going to talk about what we're doing with MPLS and how it enables federation between multiple data centers. And I'll very quickly mention software-defined WAN. This is another pretty hot area, and actually one of our customers is working with us and a partner to stitch the software-defined WAN capability into NSX. So we don't have a particular SD-WAN offering as part of NSX today, but the main thing that software-defined WAN does is it lets you build overlays across the WAN kind of the same way that NSX builds overlays in the data center. So it's a very natural fit to stitch those overlays to NSX. And so today we're partnering in that space, but it's a really nice extension of the capabilities that we've been developing for years. So let's go a bit deeper on federation. So this is a little chart I put together. Somebody asked me, given all the different multi-site options that you have, do you really need one more? Well, this is trying to answer that question. If you're in the metro space, we have a pretty good solution today that involves stretching clusters using shared storage across the metro. But that only works if you're willing to do that over pretty tight latency. Then we have a separated clusters or multi-vCenter option where you can go up to kind of continental size. Then we have a layer 2 VPN solution where you can simply build an L2 VPN tunnel between two different NSX installations, or between a simple site with no NSX and a central site with NSX. And then finally we have MPLS. So why would you add MPLS to all those other options? The main reason would be either to integrate with your existing MPLS multi-tenant backbone, which some of our customers have, or if you're a telco, to try to sort of tie your MPLS backbone to an offering to your customers, or potentially to provide a multi-tenant federated solution between two different data centers or multiple data centers that don't necessarily have a tight common administration. So let me show you how federation would work using MPLS. Again, forward-looking. This was actually forward-looking when I did it last year. It was forward-looking when I did it 2 years ago. It's still forward-looking. Who knows? Maybe next year I'll be talking about it in production. So this is an example of two different NSX deployments running in a sort of a loosely coupled environment. On the left-hand side, we use the NSX API to create some virtual networking for tenant A. And then on the right-hand side, we do the same thing. These are two pretty independent operations at this point. So we have a couple of bits of virtual network. We'd like to federate them together so that this tenant now sees he has a unified network across these multiple data centers. We can do this by running multi-protocol BGP between those two different installations. And what we would do here is we would use the capabilities of multi-protocol BGP to connect together different autonomous systems. And this gets a little bit technical if you're not an MPLS expert, but essentially there's a couple of identifiers that get advertised in BGP in this environment that lets you effectively identify which tenant is which. And all you have to do is get the two different sites to agree. When I'm talking about tenant A, I will use identifier X. And when you're talking about tenant A, you could either use identifier X or you could use identifier Y. As long as we both agree, then we can both stitch that tenant's networks together. So that's a kind of high-level view of how you could do this using MPLS to federate data centers. And you could do that whether or not the intervening network was MPLS. So that roughly wraps up the formal content. I'm just going to do a couple of minutes of conclusion, and then we'll take some questions. If you are going to leave now, which I can see a few people are doing, you do have the chance to fill in a survey and win a prize. I'm not making that up. There really is a prize. So what I want you to take away is a point that I didn't really stress in my presentation today, because I'm talking mostly about forward-looking stuff. But NSX is actually a mainstream technology now. You saw that slide that my marketing people put in. Over 700 customers have bought it. Over 100 are in production. This is not something that puts you on the bleeding edge anymore. While there is a lot of new stuff, the basic technology is very solid, and we've been doing this for a while. And part of that you see showing up in the way we're doing operations. We have a very strong focus on operationalizing NSX, and that is largely driven by our desire to support people in real live production. I hope you understand that we have some serious differentiation against any other product in the marketplace, and that essentially is because we have this incredible capability to install functionality in the hypervisor to run distributed services at scale with high context right next to the virtual machine that needs those services. That is the fundamental thing that really sort of lets us stand apart. Many other things you could do are like a feature comparison, but that is a fundamental differentiator. And the final point is that we're not done yet. We're still innovating because we keep on finding more and more things that can benefit from the architectural foundation that we have. So this is a very, very powerful capability that we have. And I think if you've just started learning about NSX this week, I hope I've given you a bit of a sense of how much capability it brings. I will say what I've said for the last 2 years. I am the most excited about this technology that I have been in the almost 30 years I've worked in networking. So I hope you go away from today's talk as excited as I am, and you have a great opportunity to learn more about NSX. Here's a few things you could do. Definitely go to see the keynote tomorrow. Martin Casado will be talking. You're going to see some really cool stuff in the keynote. Take some hands-on labs and go see some of these other sessions, which will help you get a lot deeper on some of the specifics of NSX. So with that, I think I've run through my time. So I'll thank you very much for your attention, and I'll leave it for a Q&A. Thank you. So please, if you're leaving now, leave quietly. Don't forget to fill out the surveys. Unless you hated the session, don't bother. And please line up at the microphone if you want to ask a question.
Yeah, I got a quick question about the Arista integration.
Yeah.
Is that going to support the ability to understand the NSX controllers and be unicast and hybrid, or still rely on multicast mode?
I'm glad you asked that question. The question was, do we require multicast when we interact with Arista switches or with the other hardware VTEPs? And in fact, there's no multicast requirement at all when we interact with the hardware VTEPs. That's actually the reason we use OVSDB, is so we can tell the switches everything they need to know without any requirement for multicast. So thanks for bringing that up.
I'm setting up NSX right now in my sandbox environment, and I want to know if you guys have some kind of easy button solution that checks out the configuration of all the hardware in place. I have UCS and all the networking configuration involved. I want to make sure everything's spot on. Do you guys have anything for helping out with that?
So we have a couple of things. If you actually noticed the demo that Ken showed with VROps, it actually showed like 8 things that were not set up properly. We didn't dwell on that, but those are the kind of things that VROps can check for you. So that is certainly one option to verify the correct configuration. We also have very detailed design guides for common configurations like UCS.
Yep,
So
I'm using both.
Okay.
Both of those already,
and then
it still has some gray areas. I have some questions to ask.
So I think in terms of tooling, VROps is the best thing I know of. Some of our other partner tools might also help.
Okay, thank you.
Good luck, thanks.
Hi, Bruce. So we're standing up both versions of NSX, NSX-MH and NSX-V. On your slides, I see mention of STT, which I think is only MH. Is that true?
The question was, is STT only an NSX-MH feature?
I guess my real question is, where are we going? Because it's my understanding that sort of OVSDB is an MH thing and not a V thing. And
so let me nail that one right now. So OVSDB has been on NSX-MH in demo form or something for about 2 years.
Right.
OVSDB is on NSX 6.2, okay. NSX-V. So it's on both platforms today. Regarding STT, STT is today only implemented in MH, and I think our long-term trend is to use either VXLAN or Geneve in the forward-looking approaches. So STT has a few reasons we wouldn't want to use it forever, but so the long-term direction is some mixture of VXLAN and Geneve.
So I take it the supposed merge product will be some combination of these things from a networking point of view?
Right, so you're asking about the merge product, which I'm never quite sure how much I can say in public, but your assumption is pretty much correct.
Okay, thank you.
We've got a question at the other mic there.
A follow-up on the Geneve option. Are you mandating the Geneve support on the hardware VTEPs too?
The question is, will we find Geneve support on the hardware VTEPs? Given that it's already showing up in the silicon, I expect it will show up on the hardware VTEPs. I don't know if Ken wants to comment on that at all. He said it's a matter of time and priority. It will come.
With the hardware VTEP support, is it just for layer 2 bridging or for layer 3 as well?
So in terms of what's in the product today, we support L2 on the hardware VTEPs, and all the things that I talked about, L3 and ACL support, that's forward-looking.
Okay. And follow up on that, with the layer 2, how do you handle the bump traffic replication between the hardware VTEPs and the
Yeah, that's a good question. So how do we handle broadcast unknown and multicast? We handle that basically by having a set of nodes within the NSX system that receive that traffic and replicate it where it's needed. So for example, if you had a logical switch that touched 4 different servers, then one of those servers would receive the traffic and replicate it to the other 3.
Okay.
You typically don't have unknown traffic because NSX tells the VTEP where all the VMs are.
Yes. Thank you.
Hey, Bruce. Other hardware layer 2 VTEP vendors at this point that you can talk about?
There, a man from Brocade put his hand up at the back there. So our hardware ecosystem keeps on growing so fast I can't keep up, but I know for sure Arista, Brocade, Cumulus, Dell, HP, Juniper, and I think there's a couple that I'm missing, and that list will grow.
All right. Thanks.
Yeah, all the big names. Yeah, all the big names really.
and the firewall applet that you were talking about for the physical workload, that's a future forward-looking, or that's...
Yeah, so the ability to configure access controls on physical VTEPs is forward-looking.
Okay.
As I say, you can look at how it's going to work by reading what's in OVS. That's what I showed up on the screen, but the actual implementation is yet to come.
All right, thanks.
Yeah.
Yes. How does NSX address physical-to-physical workloads, not involving any virtual services at all?
Yeah, actually, that's a good question. How do we deal with physical-to-physical workloads? And so essentially what we do there is we can do pretty much the same thing as what we do with virtual-to-physical, provided that traffic comes into some device that we touch. So for example, if it comes into an NSX edge, we could apply policies there. If it comes into a hardware VTEP that we control, we could apply policies there. So you can like all those things that I showed for physical to virtual, they actually work for physical to physical, provided we can touch the device that's forwarding the traffic between those physical workloads.
Is there any performance hit when having to go through a controller?
I'm sorry, say that again?
Is there a performance hit going through a controller?
Is there a performance hit going through a controller? No, there's not, because no data traffic goes through the controller. The controller is basically taking API requests and configuring the hardware VTEPs to do the things that you previously would have done by talking to the CLI. So it performs the same way it would do if you configured it through the CLI, but you'll get it configured much more easily.
Thank you.
Okay, I think we may be just about done with questions there. Right on time. Thank you, everybody. And I hope to see you around the conference.